We will start our helicopter aerodynamics and performance course, AE 6070, with some preliminary remarks. And I'm going to switch to a full screen mode so that you could see the screen a little bit clearly. So when you look at a helicopter, this is a picture of a helicopter looking from side view. It's a conventional helicopter, so it's got a fuselage underneath, landing area sticking outside. Some of the helicopters, you could tuck them in to reduce the drag of the vehicle, just like in an aircraft. And the rotor is right on top, and there's a hub. Inside the hub is a shaft that connects it to the engine, so the engine is what causes the rotor to rotate. And then just like a conventional aircraft, it's got a horizontal stabilizer and a vertical stabilizer for stability purposes. And there's also a tail rotor at the back. So we are going to look at some of the components and discuss what they do as we proceed into this course. The primary purpose of the helicopter rotor is to produce thrust upwards, but the rotor disc can also be tilted forward so that it also provides a propulsive force to overcome the drag. So you don't need a separate engine, although some helicopters will have an engine. But most of the time, the rotor itself will produce not only the lift to hold up the vehicle, not only the propulsive force to push it forward, but also all the forces and moments needed to roll the vehicle to the left, to roll the vehicle to the right, and so forth. You use the tail rotor thrust to control the yaw to the left or the right. So helicopter is sometimes defined as a vehicle where the main rotor does predominantly all the work of producing lift, producing thrust, producing all the control forces, and also the control moments. There are vehicles that differ from these. For example, they may have an auxiliary wing to produce some lift, or they may have an auxiliary propeller or a propulsor either at the nose or at the back. These are called compound helicopters or compound vehicles. A pure helicopter, the rotor does most of the work. Because the rotor is spinning in the American system, if you look at the helicopter, it'll be rotating counterclockwise when you look at this image. That means the rotor to the pilot's right, rotor blade will be moving forward into the air. And on the pilot's left, it'll be moving away from the air, oncoming airstream. So the V infinity is the oncoming airstream in the forward flight. So the rotor is advancing or increasing, moving forward to the pilot's right and then retreating to the pilot's left. It's cumbersome to call pilot's left and pilot's right, and therefore we will give it an azimuthal location of the blade. So in the American convention, when the rotor is over the tail boom, it's got an azimuthal angle of 0 degrees. When it is perpendicular to the shaft of the fuselage, it's at 90 degrees to the pilot's right, azimuth of 90 degrees. When the blade goes in front of the pilot, it's got an azimuthal angle. Psi is the symbol of 180 degrees. And when it reaches the pilot's left, it's 270 degrees. We should note that not every helicopter rotates this way. European helicopters, they rotate in the counterclockwise direction. Some people say this is done to conserve the global angular momentum, but that remains to be seen. So there is not just one way the rotor rotates, but we will be following the American convention in this particular course. Now, what happens to the aerodynamics of the rotor? If you look at the blade that is at a 90-degree azimuth to the pilot's right in this case, it's moving forward at a speed of omega times r, where r is the radial location. So farther out you go, the faster it is moving. So for a helicopter such as a Black Hawk, the tip may be spinning at around 600 to 650 feet per second, roughly Mach 0.6. But since we are also traveling forward, let's say 100 feet per second to 150 feet per second, you have the oncoming air coming in at Mach 0.2 or Mach 0.3. Okay. So right near the tip, these two things add up. The blade is running into the air and the air is coming towards it. Blade is moving at Mach 0.6. The oncoming air is at Mach 0.2. So these two things add up. So you get a transonic Mach numbers around 0.8, 0.85 near the tip on the advancing side. Advancing means you're advancing into the oncoming air. In this case, near psi equal to 90 degrees. When you have such high advancing Mach number, the dynamic pressure becomes very, very high. 1/2 rho v infinity squared gets very, very high. And also, because the local Mach number is now higher, you start to getting shock waves on the surface. These shock waves can cause many bad things. From undergraduate aerodynamics, we know that the shock waves can cause wave drag, increasing the drag. The shocks shift the pressure distribution aft of the aerofoil. The shocks themselves move. They sit on the back end of the aerofoil, say around 40% or 50%. The elastic axis of the blade, where the structural loads are born, is around 25% of the chord, the aerodynamic center, for subsonic flow. So sometimes you get a large nose down pitching moment, twisting the blades down. Okay. Another thing that happens is these shock waves, they don't just sit on the airfoil, they don't sit on the blade, they propagate outwards. So they propagate past the blade tip out into the air. So as the blade rotates, this shock structure moves like a sonic boom. So you hear a loud noise called a sonic boom noise in the plane of the rotor. Okay. So if you're thousands of feet away in the front, very far away, so this sound waves propagate in the plane of the rotor, so they travel large distances. Remember, this is a very, very low frequency sound wave, because the tip speed is around 600 to 50 feet or so, as I mentioned to you. The blade radius is 30 feet or so. So the angular velocity in radians is like 20 radians per second. That's like 6 revolutions per second. So it's spinning very, very slowly. Okay. So it's this low speed sound wave propagates very large distances, so people can hear it, sense you coming. So if you're a military helicopter such as a Black Hawk, this is a concern because people know you are coming. Okay. They don't need a human ear to listen to it. Microphones on the ground can hear perfectly. They can do a Fourier transform, get the frequency content, and exactly tell the observer what type of helicopter it is and what type of noise it is producing, how fast it is coming, and so forth. You can reverse engineer and get this information. On the retreating side, what happens is, which is psi equal to 270, the Mach numbers subtract from each other. Okay, so near the tip speed is Mach 0.6, but the air is chasing it at Mach 0.2. So right near the tip, you get a very, very low Mach number, relatively low Mach number of 0.4. So now we have a lower dynamic pressure. 1/2 rho velocity squared. The velocity squared now is 400 feet squared instead of 800 feet squared or a 900 feet per squared. Yes. So on one side you get a very high dynamic pressure, on the other side you get a very low dynamic pressure. Therefore, if you don't do anything to the blades, what would happen is you'll get too much lift on one side, too little lift on the other side. So the vehicle will have a tendency to roll to the pilot's left, okay, if the blade was rigidly attached to the hub. Now, pilots can do several things to control it. If you put a hinge near the root, so allowing the blade to flap up and down, then the purpose of a hinge is to transfer the lift force to the fuselage, but not the moments. Okay. Then what would happen is the blade will flap up and down. On the advancing side, it will flap up. because of the extra lift, immediately you produce a downward directed wind, so that reduces the effective angle of attack. So it reduces the CL, it reduces the lift on the advancing side. On the retreating side, what happens is the lower lift, relatively lower lift, if you have a hinge, it will cause the blade to flap down. Then air will rush from the bottom upwards, so it produces an effective upwash, increasing the angle of attack. Then it will produce extra lift. So just by flapping the blade up or down, you can balance the lift. So this is one way you could balance the lift on the left side, on the right side, and compensate for the rolling moment. By putting the hinge, you can eliminate the moments from getting transferred to the fuselage. Another thing that a pilot can do that we will see later on is to change the angle of attack by cyclically pitching the blade up and down. We call it a cyclic pitch. So the pilot can reduce the angle of attack of the blade at 90 degrees to reduce the lift. And then the pilot can increase the angle of attack at cycle to 270 degrees to increase the lift. So once per rev, the angle of attack will cyclically change up and down. Okay. So this is called a cyclical pitch control. It's a pilot action or a computer in the case of an autonomous system. So high-speed forward flight, we get shock waves on the tips, which are bad for a number of reasons. It produces wave drag. It produces a nose-down twist of the blade. It produces noise that propagates forward and away from the rotor. You have hinges, and you perhaps a cyclical pitch control to balance the load. But if you look on the left side, how about the inboard location, slightly inboard? Because omega r keeps decreasing, so the Mach number keeps decreasing. And if you have a very, very low angle, low velocity flow, and if you are operating at a high angle because of the cyclical pitch control, the blade may stall. Think of an airplane that is flying very, very slowly. If you pitch it up, aerofoil at a high angle of attack moving very fast, moving forward at a very low speed, is going to stall. Therefore, the blade will stall. So it will be dynamically stalling in and out of stall every rotation. So this is called a dynamic stall phenomenon. Dynamic stall phenomena causes abrupt rise and fall of lift. It produces its own vortex structure, separated flow over the aerofoil. It produces the nose-down pitching moment on the blades. So all these moments get transmitted to the hub. At the hub, you have control rods called the pitch links. These are the ones that pitch the blade up and down. So the pitch link is wanting to pitch the blade up on the retreating side, but the nose-down pitching moment caused by the dynamic stall is compressing the blade. So the pitch links see up and down motion, so they go through a cyclical fatigue, so they may eventually break. Okay. You may wonder, why can't I make it bigger? Remember, all those links are exposed to the air in many cases. Round circular rods, including the hub, have a lot of drag. An aerofoil has got a CD, drag coefficient of 0.01. A circular cylinder has got a CD of 1, almost 100 times higher. So the small hub region of a rotor that we see in this picture can dramatically increase the drag. In fact, it could be shown that this hub region has got the same amount of drag as the rest of the fuselage, rest of the horizontal tail, rest of the vertical tail, in some cases including the landing gear. So all these exposed regions produce a lot of drag that we have to worry about. Some of the other things that happens is the blades are extremely long, extremely flexible to keep the weight down. You don't make it overly rigid, so you make it pliable, flexible. So the blades bend up and down because of this cyclically varying aerodynamic loads. They also twist up and down because of the cyclically varying pitching moments. Therefore, you experience a lot of stresses all over the blade, so cyclical fatigue can occur. So aeroelastically, the blades are behaving. So these have to be considered. These need to be included in the motion of the helicopter. Another thing that happens is, just like an airplane wingtip, you produce a tip vortex because on the bottom side of the wing you have a higher pressure. On the upper surface of the wing you have lower pressure. The pressure difference causes a tip vortex to form. In the case of a helicopter blades, tip vortices are formed. These vortices are pushed down by the downward flow downwards that the rotor generates, that we will see a little later in this course when we talk about rotors in hover and forward flight. But they don't move very far away from the rotor disc. Therefore, they may fly immediately underneath the following blade. Now, these tip vortices are like a mini tornadoes. So as they are spinning, they are producing a upward directed flow in one direction, downward directed flow in the other direction. So the following blade may see an upwash, an increase in the angle of attack on one side, a downwash or a decrease in the angle of attack on the other side. These vortices are very, very small. So when the blade passes over it, it's like a car running over a bump, speed bump, very fast, produces an abrupt up and down lift production. It produces extra vibrations caused by the blade-vortex interaction. This abrupt change in the lift up and down also changes the pressure distribution over the airfoil. It propagates away from the rotor, usually in the downward direction and also in the upward direction. Downward direction is where the community lives, so here you hear a noise called a blade-vortex interaction noise. You would sometimes see it when a helicopter is trying to land on top of a building, or when it's descending, you would hear the sound, this is the blade-vortex interaction noise. This is very, very important. Other things that happens is these vortices will interact with the tail rotor. They will produce a main rotor, tail rotor interaction. These vortices can also hit the horizontal stabilizer and vertical stabilizer, and they may cause an interaction. In fact, the Black Hawk had a very adverse interaction between the main rotor wake hitting the tail rotor, tail surface, horizontal tail surface. So they made it not instead of a fixed tail surface, they made it a rotatable tail surface so that they could be aligned with the flow to reduce the interaction. Otherwise, the nose of the helicopter was bobbing up and down, keeping it from the flying, keeping from the pilot from keeping a straight and level vision. In a military helicopter, you want to be able to see where you are going, you want to be able to see your target. So these effects became very difficult. So the problems are many. You can keep working on it for years on end. As I mentioned to you, I came to Georgia Tech in 1982. This is 2020. I've been working on this for 38 years. And there's another 38 years, perhaps more, of work to be done, modeling it. It cannot be done by pure aerodynamicists like me. You need aeroelasticians, structural dynamicists. You need aeroacousticians, the flight dynamics and control folks. You need wind tunnel experts. You name it, all kind of groups. So in the case of an helicopter, you don't have a pure aerodynamics group. If you go to Lockheed, where I used to work, you'll have an aerodynamics group, structures group. They're weakly coupled to each other. Propulsion group. Sometimes we don't see each other except during Christmas parties. But in the case of a helicopter, you can't separate one problem from the other. It's important to solve the aerodynamics coupled to the elastic or structural dynamics, coupled to the flight dynamics and control, and then it's eventually coupled to the aeroacoustics group. So all these groups will work together under a big umbrella called the Aero-mechanics group. Let's move on to the next slide. Therefore, you need a systematic approach is needed. So you need a variety of tools. You can use simple back-of-the-envelope approaches. So in our first homework, that's what we would do. Spreadsheet can be used to model very, very simple problems with a thumb rule type of a formulas. Then you can go to MATLAB type of a script. We will do some more homework that would require you to write a more elaborate spreadsheet or a MATLAB code to solve the problem. Then once you have gotten the sizing done of a helicopter, some of the preliminary components are designed, and you want a more precise answers, then you'll go to high-end CFD, perhaps the aerofoil aerodynamics, perhaps the rotor aerodynamics, perhaps to model the rotor airframe interaction. Then you'll take the pressure distribution over the blades, pass it on to an aeroacoustic analysis to produce the acoustics analysis. And then you'll pass the aerodynamic loads to a structural dynamic solver, aeroelastic solver. When the blade bends and deforms, then you'll put it back into your CFD. Then the trim of the vehicle, that means the thrust it produces, propulsive force it produces, has changed. So you may need to pitch the blade up or down to increase the lift, to change the propulsive force. Then you'll trim the vehicle using flight dynamics software. So everything will be coupled. So in this work, we are going to look at the back-of-the-envelope approach, some spreadsheet-based approaches, MATLAB script-based approaches. We will address high-end CFD later on, but you would not have to do it yourself in this course because we don't have enough time to develop or use the tools, but I will show you some of the tools that we have developed in our work. So we will assume that you have some familiarity with classical low-speed aerodynamics. If you are not familiar, there is some background information that I have shown you in this course. I'm going to show you the Canvas website. If you go to the aerofoil aerodynamics review, some of the background information is shown in here. Okay. So I will stop after just these 3 slides, these preliminary remarks. Then we'll continue in a follow recording, additional preliminary remarks. We are by no means done. We're going to do it, continue on this in a following recording.